everyone, my name is Yeva Yeghoyan, and today my teammate Gor Sahakyan and I are going to present our capstone project, which is about bioimpedance spectroscopy system for non-invasive tissue analysis. Bioimpedance spectroscopy, or BIS, is a powerful bridge between electrical engineering and clinical diagnostics. Hence, our goal was to create a system which will have a high precision output, which will help us to understand the physiological changes of the tissues. To give you an overview of today's presentation, we will start by understanding the core clinical problem and our target groups. Then we will introduce our hardware-specific solution and the fundamental science of what is BIS and how it works. After that, we will dive into the technical implementation of our design, the block diagrams, custom PCB, and measurement results, and we will conclude with the comparison of our device with an existing technologies, an analysis of risks, as well as our vision for the future iterations. Our primary motivation was for this project lies in a significant gap in a current clinical monitoring, specifically for cancer survivors. After treatment, they face a high risk of getting the lymphedema, which is a chronic condition when fluid builds up in the limbs. In a traditional method, it can be detecting when the fluid volume is reaching roughly 300 milliliters. And by that time, the condition is already chronic and much more difficult to reverse. And that will create a wait-and-see state of anxiety for the survivors. Beyond that, our device serves for athletes for monitoring their body composition, such as fat mass, fat-free mass, muscle mass, and for tracking their overall hydration for their body. Our solution was designed to generate, inject, and measure the electrical signals at a high precision. It should generate electrical signals, inject the current, and also do a data logging. As you can see, it is a cohesive unit that integrates all of that components. We have the data which we will get from the analog hardware that we have. Then this data will be sent to the PC when our software will conduct the analysis and visualization. Unlike bulky equipment, our device will be portable, cost-effective, and will make the long-term monitoring for the health a reality for the people on their own homes. So what exactly is bioimpedance spectroscopy? At its core, it is a measurement of the flow of the body's opposition of the flow of an alternating current. We are using this frequency spectrum range from 1 kilohertz to 500 kilohertz, and we're injecting a really low level current into the human's body for about 400 microamperes. Based on the ISO standards, we're not allowed to inject more than 1 milliampere, which is also very low for having the nerve stimulation or any tissue damage. Now let's understand how it works. The accuracy of our system relies on a 4-electrode or tetrapolar configuration. We're using 4 electrodes, 2 for injecting the current and 2 for measuring the voltage drop. This is crucial because it eliminates the impedance of the electrodes themselves. Otherwise, it can skew the results. And the spectroscopy aspect of our system is that we are sweeping across the ranges of the frequencies. As I have mentioned, we're not using any frequency which is below 1 kilohertz, because in that case, the current penetrates only in the extracellular spaces, as you can see here. However, at high frequencies, it can go to the both intra and extracellular compartments.
Hello everyone, my name is Gor and I will talk about how our BIS system is implemented. As you've already mentioned, we use the tetrapolar electrode configuration, and we can depict the human body as a RC circuit with a parallel of R. So when we injecting the current through this circuit, it happens the voltage and current phase changes, and via the increasing of the frequencies, this delay became higher and higher. So every point we can conduct and calculate the reactance and the resistance of this similar circuit in the different frequencies, and get the result of the low frequencies for the extracellular and the higher frequencies for both extracellular and intracellular. Here, for confirming our measurement method correctness, we connect to our system capacitor, and which is on the left side, and you can see that we are increasing the frequency, the delay between current and voltage became more visible. And at the right side, I connect the system to my hand, and here you can see that it adds some noises because our hand is not the ideal capacitor circuit, and during the highest frequencies you can note that the phase between the voltage and the current changes as well. So this confirms the correctness of the measurement. Here is the block diagram for our system. We use the controller for controlling the function generator. This function generator is the reference signal generator for our system. After that, we need to amplify that signal and convert it to the current. Then we inject it through the body and use the analog front end, which is in this case the instrumentational amplifier. This isolates the human body for the measurement devices, and then we use the high resolution high-speed ADCs for capturing the signal for the further analysis. For the controller, we use the STM32 blue pill. This controls the function generator AD9833. So we also connect the push button. It used to start the process. We also has the LED. So when we press the button, LED turns on and indicate that the process has started. And after the process is completed, the LED turns off. As I already mentioned, we use the 9833 function generator. This is the reference, and this creates the signal from 1 kHz to 500 kHz with a sweep of 10 kHz step. For the amplifier, current pump, and the analog front end, we designed the custom PCB. Here you can see that we at the left corner, the 3D model created in the Altium Designer. At the center, we use the fabricated empty PCB, and on the right side, you can see the fully assembled and functional PCB. This is also acts as the main hub of the hardware of the system because all the parts connected to it. This is why we create the custom PCB. Here is the schematic of this PCB. Here you can see the part of the function generator, the amplifier, the current pump, the instrumentation amplifier. Also here is the shunt resistor for the current measurement and respective the amplifier for that. For the further iteration, we also add some high resolution, high speed ADCs. You can also see that we use these jumpers to isolate each component from each other because this simplifies the troubleshooting step during our project. For capturing the signal, we use the analog discovery tree device. This device has two differential oscilloscope channels which allow us to parallelly measure phase difference between the voltage and the current. For analysis, we use the LabVIEW environment for capturing the signal and for the further analysis, and also for data logging. We also use this device for supplying bipolar power supply for our op-amps, plus minus 5 volts. For the analysis, we use this call graph. Here you can see that the x-axis is the resistance, y-axis is the reactance. We have a few terms, R0, which represent the impedance in the lower frequencies, R infinity, which represents the impedance in higher frequencies. Here you can also see the term of phase angle and the characteristic frequency. These terms speak about the healthiness of the cell membrane, and they are direct proportional to each other. So higher the phase angle, higher the characteristic frequency, healthier the cell membrane. So we use our measurement and create the call graph. From the left side, you can see a graph created by our devices, which measured my body. And we use the literature information. They use the similar setup with the similar frequencies, with a similar sweep step frequency, and measure the unhealthy tissue, which has the problem with the cell membrane. Here you can clearly see the difference of the phase angle and also the characteristic frequency. It is much lower than the healthy tissue. Also, you can see the difference of the R0 and R infinity parameters. They much lower than healthier one.
So as Gor has mentioned, we're getting the reactance and the resistance for the results. After that, the most important part is phase angle. So higher it is, the healthier is the tissue. However, it is important to note that where we should integrate more tools, additional tools besides our device for getting the corrected phase angle to have fully precise result. Now we have the measured one, which is very close to the actual phase angle, but with the integration of additional tools, we will get a fully corrected one. And from that, from all of that formulas, we get the biological formulas that we need, for example, for body composition or for the hydration level. These formulas are validated from the company which is specialized in this field and have their own researches according to this topic. So we took this formula to test our measurements, and here we can see fat-free mass, fat mass, or even total body water. And the most important part of this is the volume formula, which is which has the KB constant, as you can see. This constant is crucial because it treats our body not as a uniform cylinder, but as a combination of 4 cylinders. And for the adults, there is a general constant for that of 4.3. So we just plug those values and the personal reactance, resistance, or other body parameters and getting our results.
Here is the feature and the limitations of our system. I will mention a few of them. We can say as a feature that it is non-invasive, so it is safe and painless. It is portable because we can use it in the home or point of care, whatever we need. It uses multi-frequencies compared to the single frequency devices, so it has the higher accuracy. So it is cost effective and it allow us to make the real-time monitoring. As a limitation, it requires careful calibration protocols, and it needs to complex data interpretation. Also, bad connected electrode can affect by unexpected results. So that's the features and the limitations.
Now here we can see the compare and contrast table for our device and 2 other devices which have some similarities with our device. The first one is the smart scale. The smart scale is based on the single frequency analysis, which is mostly statistics rather than personal output for the person. The last one is imaging machines, which are very good if you want the detailed anatomical details of your body. However, our device is something in between. It is cost effective and portable, and it can give you also the details of your body, not too detailed, but the hydration level or body composition if you want to track it on a daily basis. Here are some risks that we have for our device. The first and foremost one is that our device is in its initial stages of the development, and we do not have the error handling yet. So if something breaks inside of the system, the user will not get the alert of this, and this will lead to a need for the recalibration from the professional repeatedly. Also, there is a risk that even though we can detect the condition from the early stages, the doctors may not act until it is visible for them. And also that the customers can confuse our system with the treatment and miss their visit to professionals. But it is important to understand that it is not a treatment or something like that. It is just monitoring if you want to do it regularly, and it is important to have your treatment outside of this device usage.
About the future development and the iteration, we consider to change analog discovery tree with the high resolution high speed ADCs. This will allow us to reduce the cost about 80%. We also consider to add some lithium-ion batteries and use the mobile application for the data interpretation. This will allow us to make the device more independent from the PC or the laptop. And as we use the 3D printing for the prototyping the case, we plan to change in more durable one. So in addition, during the poster presentation, some people from the Orbally approach us and make an offer for collaboration. They made a device of high voltage to inject the cell membranes. So their device don't have capability to measure the impedance, and our device has. So they plan to collaborate and integrate our device to their systems.
To conclude, we have successfully built a device which is non-invasive, portable, and cost-effective for monitoring every health metric that you need in your everyday life.
Thank you.
Great work.
Thank you.
And can you go with the slide back where you have the problems list that you have mentioned? Right.
Risk.
Yeah, this one. Have you done some risk mitigation study of like for the listed items, any thoughts of how you can mitigate in a next iteration for the device, let's say?
How we add
What we will do at the first stages?
Well, no, you have the device right there, right? And you have the list of your technical risks, right? So have you done any mitigation study of how can you, in the next iteration, let's say, fix or partially fix or resolve any of these risks?
So we can partially fix the risk of, for example, the error handling part, because we can integrate the hardware and the software part to make device every time test self, and after if it gets some error, it indicate the user there is something wrong with the device, so you can't use, or it need calibration before using. So that part we can eliminate in the future iterations.
Also, maybe when it will be medically validated, so doctors will trust the device and will take some measures to do something for preventing the condition to the worsen situation.
And also, you mentioned one of the existing devices is using statistical data.
Not one of the smart scales, because they are based on the single frequency, which cannot have the precise information because it is working on the one frequency range, and they are using the statistics. For example, at this gender and age, the normal for the men is, for example, 45 kilograms, and for that weight you should have this kind of fat-free mass. But our device analyzes a lot of range of frequencies, and it is more precise and more personal for that person.
So what I'm saying is that there's a clear evidence that the statistics brings the value to this, right? So have you thought about adding the statistics on top of what you have done? Is it possible to do, or have you thought about it?
For this device, there is no need for the statistics to be implemented because it has the ability to measure the intracellular parts, which is the most important one. The single frequency ones do not have that ability. That is why they are using the statistics.
So that doesn't make any sense to add on top of what you have in statistics.
After getting the outputs, when we use the result parts of fat-free mass, there we use the statistics of the
of men and women for the same company from their researches to compare which values are normal for the healthy people and for the unhealthy ones. So we used statistics there.
Well, given that the device is primarily oriented to the pet customers, we have some clinical condition, like the introduction we mentioned, cancer survivors or post treatment dehydration, rehydration issues that is seen to help to solve. I think you should think about making a wearable product for the patient to carry on to himself or herself, but that your device parameter doesn't help. You have mentioned in the paper that it works between 15 and 30 degrees Celsius, whereas the patient can have up to 40 to 41, and we should think about it because if we are looking at the immediate changes in hydration levels, which the patient has to pay immediate attention, then this has to be taken into consideration.
Of course.
As a development advice.
Thank you very much.
Small question, please.
Probably you mentioned, but regarding the analog circuit, as probably most of it is about the PCB, as the device you said should be very accurate, so the measurement should be precise. You will have area for errors. Have you done any measurement, or do you have any considerations of having some of reducing the interference of the other components on the analog circuit, or adding some shielding or similar stuff, because the sensitivity is very important.
Because this is primary the POC of the concept, we take into the consideration and the future development. We will add some circuitry to add the accuracy of the overall system and also make the device more precise when it does some measurements.
And it could talk to the experts that you maybe the officers say Popeka interested to have this monitoring. When we say this monitoring, it means that during the time you have measures, and this measures should be somewhere to understand the dynamics, etc. Is there any interface? First of all, what Docker would like to see, and what is the timing in the time scale? How you provide the values? Chance probably.
As we already mentioned, we have some interface. We use the LabVIEW environment.
LabVIEW, I know LabVIEW, but LabVIEW is just for capturing and providing the.
This also can we also LabVIEW for logging this data, so it can be used in the further investigation of the problem for the monitoring. Or am I understand your question
Yeah,
correct?
I think so, but doctor will not accept it. That is lot. I understand that if you're collecting it, capturing it, then one day you will provide it the.
Of course,
To the
we
cloud.
plan to change the analog discovery with the high-speed, high-resolution ADCs. So for the further implementation, we will use another software and for capturing and data loading.
Okay.
Did you test it on several people or
We test it on me.
only on you?
Yeah, we're
Yeah.
not permitted. It is
Okay,
not
but
permitted.
I think one thing is that maybe you need to have a supervisor, like someone from medical field to understand this field, but also the skin thickness, the color of the skin, everything will impact the accuracy of the result that you have. So that's important. You test on several people, and then maybe you need to make changes on the design, amplifier, and things like that. So if you do more tests, again, you will get more accurate
Of course.
design and
Mhm.
results.
But and if I can just add to that, even calibrate against other data
Mhm.
approaches. In other words, you can get a sense of what your variance is for a given person compared to alternative sensors.
Mhm.
Also directions to maybe ground your work a little more in context.
Even the moisture of the skin can cause the.
Right. Right. But instead of qualitative judgments like that, you can actually get
So there is.
how the variance and what's the standard deviation or with some basic statistics on
Mhm.
I did 100 measurements morning, noon, night, dehydrated, hydrated, I ate, I didn't eat, I don't know, whatever all the factors that could be. Okay.
Okay.
Thank you.
Thank you.